So welcome everyone to the I2K 2020 tutorial on modern insights from microscopy images, web-based methodologies. My name is Matt McCormick, and I will be the instructor for this tutorial. This is an interactive tutorial where we're going to be discussing modern web-based methods for bioimage analysis and how we can use these methods for working with extremely large images to improve the reproducibility of our research. And we're going to go through some of the concepts, the approaches, and the modern open source tooling that can help us achieve these goals. We're going to start with the fundamentals of web-based imaging. Then we're going to cover visualization, image data storage for the web, and distributed image processing in the cloud. If we have enough time, we'll go into reusable components for imaging. And these sessions are a series of Jupyter notebooks. There are updates. You should have the link. It's also in the Slack. We have a Slack channel in the I2K Slack. You should receive an invite, and then you can join the channel by clicking the Add Channels and searching for the Web Methodologies tutorial. The notebooks, there are 6 different notebooks with 6 different sections. We'll start off with an introduction to some of the basic technologies and background on some of the technology. Then we'll have some introductions, so you can introduce yourself to your peers here and explain what you're working on and what you're really interested in, what you'd like to get out of the tutorial. We'll talk about web-based visualization, and then we'll talk about image data storage that works well for large images and the visualization and distributed processing that we're going to do. Then we'll go into distributed image processing, and you'll spin up your own personal cluster in the cloud and run it in some analysis in the cloud. And finally, we're going to touch on components, plugin components that can be composed to create an application. So let's start with the first notebook. If you're still getting the software environment up and running, hopefully you'll have it running by the end of the session. If not, we'll go over, I'll help you at the end of the session. We're going to have a break, 5 to 10 minute break between each session. But this first session is a little longer, some background. At the end, we'll do exercises at the end of each section. So the learning objectives for the introduction are to explain what we mean by modern web-based image analysis methods. Then we'll go into some of the technologies that are relevant for bioimaging and reproducibility. And then we'll talk about how these new methods fit with the old open source software that we use for imaging. So what do we mean by this modern web-based image analysis? In this case, the user interface is going to be your web browser in all cases. And we'll be communicating, sending data, sending applications on the internet, primarily through HTTPS. And in this case, computation can happen locally on the client, which means we're using the term client. That means the computer that you're running the web browser on, or it can happen on servers that are hosted in the cloud. And the important technology background. So the first thing to realize is that browsers have changed dramatically in the last few years. And there's this concept of evergreen browsers. An evergreen browser means a browser that releases frequently, and it strives for up-to-date and comprehensive support for the web standards. And a few examples include Google Chrome or Mozilla Firefox, Microsoft Edge, Opera, and Apple Safari. Those are the main browsers. Note that Chrome, Edge, and Opera are all based on the same underlying open source foundation, the Chromium open source project that implements all the standards. Presently, Safari can sometimes lag behind or it's limited in its standard support, but it strives to have standard support. Until a few years ago, Internet Explorer was also a large market share of the browser community, but it's no longer supported by Microsoft as of next year, and support is going away. And it doesn't have many of the modern web standard features that we'll be talking about today. A lot of the features that allow us to do high performance computing, large image processing with browser tools requires these modern standards. Are there any questions about browsers or comments of browsers? Okay, so next let's talk about how do you compute, how do you program for the web? And the one takeaway that we have for this section is that you should learn JavaScript. That's the one takeaway. Take home. JavaScript is the language of the web, and knowing some JavaScript, if you don't know it already, will be a useful skill going forward with your work. Just kind of giving back an idea of people's experience and their backgrounds. Can we go around the different group and explain your background? Have you ever programmed JavaScript before, and what is your experience with JavaScript? Sarah, would you like to start?
Sure, I have no experience with JavaScript. I know a couple of other ones, so I guess from reading it, it doesn't seem like too tricky, but I have no actual experience with it.
Cool. Simon?
Yeah, same goes for me. I'm coming from a math background, so I just did Python and MATLAB.
Cool. You? I don't think your microphone.
Oh, okay.
Oh, now I hear. Now
Oh, cool. Can you hear me now?
Yes. Now we can
Okay. Okay, cool. Yeah, I'm a second year PhD student in biophysics. So I learned about MATLAB, Python, but I almost forgot Python because I learned like 3 years ago. So yeah, that's my experience.
Great. And Python?
Hello, hi, I'm from Los Angeles. So yeah, I have no experience with JavaScript. Yeah, I'm a biologist mostly, and I'm doing some computational genomic analysis. So we mostly use R, Python. Yeah, so yeah, I have no experience with that.
Great. And can you unmute yourself? Ritvik?
Yeah, I also have no experience with JavaScript, but I have used Python, MATLAB, and I do program often, but looking forward to learn more about JavaScript specifically.
Great. Andres?
Hi, yeah, I have extensive experience with JavaScript and also Python, so I'm coming from the software engineering side, not the technology side. So yes, my portfolio is quite distinct to me, but not really
Excellent. Prayas?
Hi. I do have some experience working with JavaScript, though I forget now what are the main things I used to do
Okay.
there. But yeah, I can pick up.
Cool. Cassandra?
Hi, I also don't have any experience with JavaScript. I'm a biology field student, so I mostly just work with R. Yeah.
Great. And Pra?
Yeah, actually, I'm also a biologist. I work with different kind of scripts, but not the Java specifically.
Great. So that's wonderful. So hopefully you'll get a lot out of this tutorial, and I think you're all very smart people, and JavaScript is one of the easier scripting languages to pick up and learn. So it's definitely within your capabilities, I'm sure. And I think Andres has some experience, but this tutorial is right for you if you have experience in R, Python, or MATLAB. You are well on your way. So a little background on why is this so important? Why should we learn about this scripting language? Why do you care? How does it relate to your cells? It's the only language with ubiquitous support across modern web browsers and all web browsers in history. Modern JavaScript runtimes, though, they've always supported JavaScript. In the last 5-10 years, they've gone from something that can be used to manipulating elements on a web page to actually running computation that we can do to help us do research and understand data. It runs in your web browser, but recently it also can run server-side, so you can run it server-side like Python. The most popular runtime is called node.js. Sometimes you'll hear it just called Node. And that runs on a server. It has the largest software package ecosystem, open source package ecosystem out there. The package manager and the registry and the command line interface to the package manager is a little confusingly named. They're all named NPM, the Node Package Manager. When you install Node, the server-side runtime, it also comes with NPM. And NPM is what you use to install JavaScript packages and libraries, and then you'll typically build those together into an application. And then every time you go to a website, you're downloading essentially an application, which is all the JavaScript that's running and provided by the server. You'll also hear the term ECMAScript, and how does that relate to JavaScript? They're essentially the same thing. ECMAScript is the standard for the language, and it was stagnant for many years, but in recent years, the language has evolved rapidly, and it's been adding new features, and every year it gets these new features, more convenient, nicer syntax, more features for scientific computing. Relevant for scientific computing. The latest version is ES 2020. And one of the most wonderful things about JavaScript is that it works everywhere. But how does it work everywhere if the language is evolving? And you might have a user who's on has a browser that's an older browser. How is it going to work in that browser? So in practice, what happens is when you're building an application for a website, the client-side code will take those JavaScript libraries and transpile them down to an older version of JavaScript, typically version 5. And version 5 came out a decade ago. So all browsers support it. And then for new language features that aren't supported, it provides polyfills, they call them, kind of shims that provide that functionality of the newer language. More recently, though, with this evergreen browser movement, now that browsers tend to keep up with the latest standards in a faster rate, people have started to reduce that practice, and they'll still transpile some of the very newer features that they're building for, but it might be just for a few recent versions of the latest browsers, the latest browser versions. And this is there are many JavaScript developers. It's guaranteed that there'll be many more JavaScript developers. And there's a lot of wonderful resources to help learn JavaScript. The best one to be aware of is the Mozilla Developer Network documentation, MDN. This is what the documentation looks like. There are tutorials, there are references, there are tools and resources. There's a lot of very nice references for the built-in objects and functionality with examples and notifications on browser compatibility and pointers. Use this resource. Something to be aware of is that when you are Google searching, you might come across the W3C schools documentation. This is also helpful, but if you can seek out the MDN documentation, you might be better served. Is there any questions about JavaScript? So JavaScript is the language of the web, and there's been many other languages that are sometimes used for building code for the web browser, and they're all transpiled down to JavaScript since that's what browsers support. There's been many kind of fad languages, and there's many languages that are in prominent use. One of the most important ones to be aware of is called TypeScript. And TypeScript is a superset of JavaScript that adds optional static type definitions. If you're familiar with the recent additions of types to Python, it's very similar to TypeScript to JavaScript. It's very similar to the recent Python typing that was added. Or if you're familiar with other strongly typed languages, that's the case. TypeScript is becoming more and more prominent, especially for libraries that are being developed and published on NPM. When you transpiled TypeScript to JavaScript when building these applications, the types in the functions, so we're passing in a floating point number, that can be checked at the compile time, and that helps avoid errors. There's also explicit types in the functions, and that's a documentation advantage. So you know what type of variables you are supposed to pass into functions. So it's something to be aware of. If you're creating a new project, you might want to learn TypeScript. It's used by many projects. There is a challenge sometimes, though, because TypeScript projects need to build on other TypeScript projects to know the types that they're supposed to be using. If you're building against a JavaScript library, you might have to create explicit external type definitions for the functions and the objects that don't have these types. But this is something to be aware of. Any questions on TypeScript or comments? And moving about, so then to move on beyond TypeScript is WebAssembly, which is a recent standard that was developed, and it's important for imaging because it allows high performance computing and allows us to reuse code that we've written to do other types of processing written in other languages like C and C++ and Rust and Python and R and Java. What is WASM, WebAssembly? It's a portable compilation target that enables deployment on a web browser, or it can be used on a server too. Unlike JavaScript, which is a plain text scripting language, essentially you send the plain text script to the browser, and during this compilation project, sometimes they can reduce the size of those scripts, but it's still plain text. WebAssembly is a binary format, and so there's less data to send to the client when you visit a web page, and it has better efficiency because there's less code to compile by the client when it receives that binary code. It also supports other things on hardware that allow it to run faster, hardware features. And at the same time, it focuses on a secure, memory-safe sandbox execution. So there's no security vulnerabilities. So when you visit a website, you're essentially downloading a program when you visit a web page, and that program doesn't have access to your passwords and other important information on your machine. It runs in the same virtual machine as JavaScript, and it's debuggable in browsers. And currently it's been supported by all major web browsers. And it aims to be backwards compatible and forwards compatible. And although WebAssembly is not JavaScript, the way you start up a WebAssembly program and talk to a WebAssembly program is through the JavaScript API. So everything comes back to JavaScript again. Any questions about WebAssembly? So let's look at a few other technologies that are important for visualization and high performance computing or accelerated processing. Those are WebGL and WebGPU. So WebGL and WebGPU give access to the graphics cards that provide greater performance and also 3D visualization capabilities. WebGL is the current standard that's supported by all major browsers and allows you to do 3D graphics. WebGPU is a new standard that is undergoing standardization. The next generation of the WebGL standard, a new standard with a different API and supporting some of the new drivers on modern GPUs. Web workers are another standard that's important for imaging because they allow us to do parallel processing. A web worker is the equivalent to a operating system thread. So with web workers, we can process on multiple cores on our computer at the same time. And finally, service workers are another type of worker. There's many types of workers in the web standards. And this service worker acts as a proxy between the web browser and the broader network. So when your browser page, your tab, asks for a network resource, asks for an image, or maybe a JavaScript piece of data, it can go through this service worker, and this service worker can decide to either present that image or that script from its cache, or it can go back up to the network. And this allows us to improve performance through caching, but also make a offline capable app. So even if you're not connected to the network, if you visit a page, it can still run like an application. And so those are all client-side technologies. those can optionally be coupled with server-side programming languages, and common choices there for imaging are Python and Rust and JavaScript and C++. Any questions about WebGL or some of these other standards? So other technologies to be aware of in this whole ecosystem are the storage, but we're going to have a special section on data storage for imaging and cloud computing. But we're going to have another section on cloud computing. Other terminology that you might hear when you're doing this work is REST. And REST is a way of communicating over HTTP. You'll hear the term RESTful APIs, and that's how you request information and get information and transmit information over HTTP over the network. And what this means is that there is a scheme for URIs, so domains and origins, and then there are standard methods for retrieving state and modifying state. And then those are methods are things you may have heard of, like get and post and put and delete. And then there's a media type that defines what type of data you want to get from the resource. That might be JSON data, for example. That's the standard way to talk over HTTP. You don't need to know the details, just that if you encounter that, you're talking over HTTP. Another technology you might hear is WebSockets. And WebSockets are a more performant way to communicate than HTTP. It opens up a two-way communication channel that allows transmitting data back and forth. And with HTTP, every time you want to transmit data, it's stateless, so you have to have a handshake and you have to verify that the data was sent. WebSockets are sort of an open communication layer that gets open between a web browser and the server. It's used in systems like Jupyter that we're using today, Colab, and other ways of sending data. Finally, a new technology to be aware of that is coming for storing and transmitting these very large data sets that we might be working with is IPFS. And this is a protocol and peer-to-peer network for storing and sharing data in a distributed file system. So think BitTorrent, but just kind of a modern standard protocol that is using these ideas of hashing and a distributed network that's an alternative to HTTP. So any questions on communication? So why do we care about this, and why is this helpful for us? Well, when we want to do large imaging, these characteristics are very advantageous, especially because it is conducive to remote storage. When you have storage either on a microscope, near a microscope, or storage in the cloud, these technologies help with that situation. However, it's important to watch out for data and compute locality, meaning the processors should be close by physically or in a network sense where the data is stored. That is a critical characteristic for performance because the overhead of transmitting the data can also be higher than the amount of time it takes to do the computations on the data. And the other characteristics of this web-based system is that the data can be stored in small chunks from an image. So if you have a very large image, it can be stored in small chunks. And these chunks are fetched on demand for analysis or visualization. Meaning you don't have to transfer the entire data set before you're able to inspect any aspect of it. And when things are stored on the web, compression is often used, and that's helpful for some very large data sets. What is really exciting is also the capability for reproducibility and ease of use. So since these are standards-based ecosystems, it's truly write once, run everywhere, and there's no installation required, no extra installation to run computation and reproduce the computation. And these standards are supported over the long term, decades, and without any maintenance costs, and that helps too. And they're also distributed, and that means that storage resources or compute resources those resources are shared by people who are using them and the people who are providing them, which makes it more sustainable. So this was a kind of a longer introduction, but now we get to our first interactive section. So you can run this cell locally. And this is just going to display in an iframe, which is kind of embedded web page in your Jupyter notebook, this interactive figure that I created maybe 5 years ago, describing a published image denoising technique. And you can try out this web page. You can select figures from the paper, and it will run in your browser and produce the output that the paper said it would produce. You can change the parameters of the execution, which will change the result, or change the input. I'll try this. So what is really interesting about this is that it was created 5 years ago and hosted on GitHub pages. So it's a free resource for hosting it. And thousands or millions of people could have used this. They could have run this code, reproduced this image denoising techniques results, tried it on their data sets, but there's no extra maintenance required and there's no extra installation required over 5 years. So kind of an example of how compelling this can be for reproducibility. And how does these new web methods, how do they relate to your existing tools that you might work with that are desktop applications, for example? So you can reuse a lot of these existing tools and bring them into a web context. There are many projects that have started to do that. One is ImageJ, and there's another I2K 2020 ImageJ tutorial. I highly encourage you to take that tutorial. This is a plugin powered hybrid computing platform for imaging and deep learning that supports these client-side JavaScript plugins or Python-based plugins and allows you to combine them together. Another example is ImageJ.js. So you've used Fiji or ImageJ on your desktop, I'm sure. But this is a version that was compiled to WebAssembly, we were talking before. The Java code, the same Java code was compiled to WebAssembly. So you can run it in your web browser on any platform, phone, tablet, operating system, and execute it without installation. Another example is I2K.js. So I2K is the Insight Toolkit. It's a library for image analysis used in medical imaging and microscopy. And this is a tool that allows you to compile I2K or other C++ code into WebAssembly and run it in this JavaScript runtime environment. Similarly, Pyodide is another project that takes Python libraries and compiles them into WebAssembly. Scikit-image, use that. And then there's these Jupyter interfaces. So Jupyter, which we're using today, it allows you to bring in many different programming languages into a web environment. But special Jupyter related projects that to be aware of are Jupyter Lab, which is the next generation browser interface for Jupyter. And because JavaScript is so important, Jupyter Lab is really built on JavaScript, and it's really a JavaScript application. So if you want to make extensions to Jupyter Lab, again, learning JavaScript, kind of the theme of this section, is a good idea. Jupyter Lab is written in JavaScript and TypeScript. So if you know TypeScript, that's good too. Colab is another alternative Jupyter Notebook interface with GPU hardware support and Google integrations. And another project to be aware of is Voila. It allows you to take these Jupyter Notebook applications and create standalone web applications from them without the coding environment to provide to your biologist friends and companions who are scared off by code. Are there any questions or comments on web-based methods here? This is a little longer section. Okay, so let's get to the interactive part of the tutorial, which is the exciting part and very interesting part. I think this is probably one of the most enlightening parts of the tutorial. We get to explore the web browser development environment. So you may not have known it, but you have an amazing developer tool in your web browser itself. We'll start with a hello world, so we can run it in Jupyter, run some JavaScript code by adding this to the top of the cell. And then the JavaScript print command is console.log. So run this cell, run that locally. And when we run it, like many other Jupyter commands, we don't see, unlike many other Jupyter commands, we don't see the output below the cell. So where did it go? It went into your browser's developer tools. And Chrome and Firefox and Edge, they all come with very nice developer tools built into every browser that you download. You don't have to do anything special to install it. So open that now in your browser. On Chrome, you can go to the menu up top, select More Tools, and then Developer Tools. Firefox is similar. Control-Shift-I is the shortcut. So open up the console. You'll see many different tabs here. It opens up in the same web page. These tabs are different tools that you have. And there's even more tools that ship with the browser. You can enable them and select them in the menu here. There is you can choose where you want to dock the tools. And the main tools to be aware of are the console. So that's a REPL, kind of like the Python REPL, where you can see the output. So here's our console.log output. That's where it came. And other scripts running on the page, they print out stuff like that image denoising application, it was printing out information here. You can see what's printed out here, and you can also run commands in the console here. Okay, so we can run something new there. So for our first exercise, output to the console a new hello world message. Then learn some new JavaScript syntax on arrays. So create a JavaScript array. The description can be found here on the syntax with two elements, 3.0 and 8.0. And then create a JavaScript float32 array with two elements, 3.0 and 8.0. So
sorry, are we supposed to have these exercises in our notebooks? Because mine stopped after the denoising.
yes, you do not have this content here.
It goes through the GitHub denoising thing and then it just stops. Did I do something wrong? Like, yeah, it gets to there and then nothing.
Do you have this content in your notebook?
No.
No?
Sorry, am I the only one? I just downloaded it from GitHub.
Let's see. Does anyone else have that issue? Yes.
I don't, but I don't have the very recent version from GitHub.
Let's see. Maybe try downloading it again.
Okay, I did something wrong. I'm sorry.
That's a good question. No, that's a good question. Okay. So try that first. And then after you've figured that out, we will try the elements inspector. So this is another tool here. Next to the console tab is the elements inspector, where you can interactively introspect DOM elements, the elements on the web page, the HTML elements, by cursing over them or clicking this button to the left of the elements tab and then clicking on an element in the page and see what happens there. And then finally, your web browser also comes with a full-featured debugger. And that is either in the sources tab or the debugger tab, depending on whether you're using Chrome or Firefox. And that will, you can set breakpoints, walk through code, see what's happening in your code. So you can go there, open up some HTML, click on a line number to set a breakpoint, and then refresh the browser to stop at that break, through it, step through it, inspect things. And as a bonus, we'll work on these exercises. And if you get through those, you can take a look at some of the other tools. So there's performance profiling tools and other really interesting tools to investigate. So let's take 5 minutes and try these exercises. 5 to 10 minutes. Let's take 8 minutes. How about I compromise there? All right. Did anyone have trouble getting into the console and creating the hello world output?
She just woke up 1 second ago.
And was everyone able to create a JavaScript array? So JavaScript array is similar to a Python list with 2 elements. Andreas, could you help us either by telling us or putting in the Slack channel what the syntax is for that? I can't hear. My audio. It's my problem. Can everyone else hear it? Andreas? Yes. Let's see.
Oh, sorry. Somehow my microphone got switched.
Good now.
Okay.
Oh, okay, I'm sorry, Andres, I lost my audio there for a second.
Well, I guess I switched to a different microphone, or Zoom switched me.
Cool, I got you now, I can hear you now. Did you take over drawing or some other tool here? Or I'm just feeling hard on Zoom. I cannot see the screen. Do you guys see the screen? Let's see. Can you share your screen, Chris? The answer?
Want me to share my screen?
Can you share your screen?
Sure. There's not much in it, but okay, sure. So
Great.
Going to the console. Oh, lost it. This must be different. Had it here earlier. Well, what I typed earlier has disappeared, but I can type it again. I forgot what the numbers were.
Great. So very similar to a Python list. And great. So that's very good. So that's how to create the 2 arrays. So you see in Andres' console there, a representation in the output of the arrays. They look similar but different. If you click on the drop-down tab next to each of one of them, what do we see? Yes.
Okay. Here you go.
Great, thank you. So we see here that there's the buffer, byte length, byte offset. So these float32 array, this is a typed array. So this is kind of a binary block of data that's more suitable for storing image pixel data than the list above. So it's going to be more performant. It's a block of data with a type, specific type for each component, pixel component. And this is a newer feature in JavaScript and the web browsers. And So if you can access the elements just like you can do in Python or NumPy. So the analogs in Python of the array are a Python list, and the float32 array is a NumPy array. That's kind of the difference. And when you do x of 0 there, we get 3. If you do, well, I'm going to take the screen share back. Thank you, Andreas. That was very good. And can I continue here? Something to note is that we create a variable x. We can create an empty array like this and set 0 to 3. The first value to 3. We look at x. It's a float32 array. And there's a keyword type of in JavaScript. And the type of x is an object. In JavaScript, there are primitive types, and then almost everything else is an object type, kind of like Python. And if you do type of 3, it's a number. And when we do type of x of 0, it's also a number. So the types of the objects are dependent on how you look at it. If we wanted to get back another float32 array, we can go to the documentation and we can see that you might have to use a function like subarray to instead retrieve back a subarray of the same typed array object. So x subarray returns a float32 array. Okay. Any questions or comments on using the console? And was everyone able to use the elements inspector? We are going to use the elements inspector in a future section, so it's important to make sure you have a handle on it. You'll notice there's this tree of the different elements that represent the HTML that comprise the page. You can expand and collapse them through these arrows on the side, and they can be selected and it'll be highlighted where that element exists in the page. It's selected in the developer tools, or clicking on this arrow and just mousing over and clicking, we can select a specific element. On the right hand side here, we see the CSS properties, the style properties for the element, explanation of what they mean here. We can actually dynamically change these. So we can maybe select a text field, and then you can change the color there on the page without having to reload the page. You can change the color to a different color. So the browser is very dynamic, and we can edit the state of the web page or the state of the JavaScript that's running with this console or these developer tools. If you are working on performant code, you can also use this profiler that comes with the browser. Or you're having trouble getting data, network requests, this network tab is also extremely useful. So that concludes our introduction. We will now take a break take a 10-minute break. The first section is a little longer. The next section, we're going to do introductions. So the goal of this section is to meet some of our peers, have a little socialization in this pandemic, and learn about what everyone else is doing, learn about your goals with this tutorial, what you'd like to get out of this tutorial, and maybe learn about some opportunities for collaborations. If you click on the notebook, there should be session 2, and clicking on that link will take you to an editable markdown page. And inside that page, you should find your name there. And beneath that page, if you have some time before we get back from the break, you can start to put maybe a description of some projects that you're working on and really what you'd like to get out of this tutorial. Put a little example there for myself. And when we get back, we'll introduce ourselves, where we came from, what type of imaging we do, and what we're interested in web-based methods. So let's reconvene in 10 minutes. All right, folks, let's get started again. So let's do little introductions and get to know each other. I'll start. My name is Matt McCormick. I am here in sunny North Carolina in the US. I work at a company called Kitware, where we do open source scientific image analysis and other open source scientific computing in a collaborative way with commercial and government and academic collaborators. I work a lot on the Insight Toolkit, a library for n-dimensional image analysis. And recently I've been doing a lot of work on multi-scale web-based image visualization. Sarah?
Hi, I'm Sarah. Sorry, I'm actually signed in twice to this Zoom because I had to switch computers because my house is always very, very loud. I have a 1-year-old, so everything's loud. I work at the Lohrey Institute for Immunology in San Diego, and I'm in the core facility. So that means I work on a lot of different projects with a lot of different people. The major challenge I'm running into right now is with everyone working at home, people need ways of analyzing data at home, so need access to web or cluster-based solutions in some way, and I'd like to help them with that.
Fantastic. What are you doing so far for that problem?
We have a internal server that people can VPN into, and just kind of so they like can VPN in to get the data, and then VPN into, we have some like workstations, but it's really, really slow and really painful, and just oftentimes it's easier to go into the building than deal with that, and that's not great right now.
Definitely, now is the time to experience that. Okay, who's next? These are the folks here. Talia? And on Charlotte. Charlotte? Let's see, I'm not hearing your mic. Is anyone else hearing on?
Do you all hear me?
Yes, yes.
I've got some problem with my computer, I don't know. So I'm a French PhD student in the second year. My thesis subject concerns the development of the microelectronic tool to study a parasite, in intestinal parasite. The name of the parasite is Cryptosporidium. It's a parasite causes diarrheic disease in humans or animals. And my objective or goals is to develop a macro device adapting to the standard of pharmaceutical industry. And for the moment, I've got a prototype to test some drugs, and so that's it. It's my goal is to test some drugs on the parasites and find the treatment.
What type of imaging are you doing? What imaging modality are you using? Maybe
What imaging?
Yeah.
All my data is fluorescence microscopy. But it's with the tool I developed, I need to use a bright field because fluorescence is not adapting to cells in the long term because I want to follow the entire cycle of the parasite.
Wonderful, thank you. Katrina, you here? Cassandra? No, Cassandra. Sasha? No. And you?
Yes, can you hear me this time?
Yes.
Okay, cool. I'm a PhD student in University of Minnesota. So I'm just in Minnesota right now. And I was a physics student, so I just transferred to biophysics field from this year. So I'm only like starting to learn about the single molecule localization microscopy. So for now, I don't have a specific project to work on, but I'm just trying to do like to image the one protein which is called ARI1. It can respond to like stress. So I use like different stress. I can like stress the cells and see the clusters of the ARI1. And also I can do some single molecule tracking for the data. So this is what I'm working on now.
Excellent. Mirat, I don't think you're here. Rashid? No? Mithan?
Hi, so yeah, I'm joining from Los Angeles. So I'm a staff scientist at UCLA, and so I'm working on a couple of projects, but one of the projects is like studying the differences between proliferating cells and non-proliferating cells. So before the shutdown happened, we generated a lot of sequencing data. So right now I'm kind of analyzing a lot of that. So like RNA-seq, ATAC-seq to learn about like gene expression and chromatin accessibility. But we want to continue that and study, like do some imaging of the nucleus, like to study like nuclear size, shape, morphology, and also like imaging a lot of histone marks and stuff. So let's get the distribution pattern. So yeah, so we started doing some confocal, and we want to do like more like super resolution microscopy, and I'm also mentoring a lot of students. So actually they are not at here, of course they're at their homes because the quarter is online. So these web-based technologies will be useful because they can use that from their homes. So that's another.
Excellent. Simon?
Hi. I'm doing my master's in computational mathematics in Germany, and I'm currently working on curvature estimation using integral invariants. Basically, we have very big point clouds, and I'm doing the curvature estimation on those at the EBI in Cambridge. And as my second point, I wrote down developing or adapting mathematical tools to solve problems in image processing. And this sounds very vague, but as long as it involves 3D image processing and useful applications, and especially nice mathematics, I'm happy. And I haven't quite found my real focus area yet. I've been trying around like denoising, segmentation, classification, and now I'm doing curvature estimation. And I started this workshop just because it sounded interesting and I like learning things. So I was like, yeah.
Cool. Very cool. Priyas?
Hi. Yeah, I work at 10x Genomics. I've been working on processing cyclically imaged 3D datasets. mostly fluorescence microscopy. I'm exploring ways to visualize it efficiently as well as work with them efficiently. So yeah, nice to meet you all.
Nice to meet you. What do you mean by cyclically there?
Sequentially, I mean.
Let's see. Okay, so over time.
Yeah.
So, okay. Great. Andres?
Hi, I just joined 10x Genomics, and so my task is to come up with an image viewer for all the images that we have from all the various microscopes. And so I'm looking how to integrate an open source project for doing that, and we'll probably do Visa, but it really depends on what common image format we standardize on, if it might be OME, TIFF, OME, ZAR, or something like that. And one problem that we are going to have is that all our images have to be registered, and then we have to figure out how to do the best transform to make this registration happening.
Very interesting. Oh, what was the institution that you're at?
10x Genomics.
Can you describe that more, or can you put a link to that? In the...
We do DNA sequencing, the same as Reyes.
Okay, great. Great. Yeah, I do a lot of work in image registration, and we're going to talk about OME-ZAR and N5 in a little bit, but kind of one of the things I've been talking with other folks in the community is the metadata that's important for registration related to spatial location, the spatial location of images relative to one each other, to another, which is very important for registration and also for multi-scale imaging.
Yeah, very interesting. Yeah, I'm just starting in this area, but I've already been told that afferent transforms are insufficient because of the way how the samples are prepared, so they might end up stretch or things like that. So it's definitely going to be a challenging problem.
Yes, yes. And yeah, I won't go into too much of a side train, but you know, we should keep in touch because I'm doing a lot of work for the very large imaging. I have a grant that hopefully will get funded next year, but maybe it'd be great to maybe work on some of your data sets for if that grant does get funded for large deformable registration.
Yeah, sure. If you have my email, so yeah, please drop me a note. It would be interesting to stay in touch.
Fantastic.
Yeah, definitely. Yeah, let us know.
Cool. And Ritvik, are you the last person?
Sure. Yeah. Hey everyone. I'm a scientist at the Allen Institute for Cell Science, and at Allen, I'm primarily interested in ways to visualize large 3D images as well as storage, and also more generally how to develop and share deep learning models on these large images. So efficient ways to share them and reproduce them easily is, I guess, generally what I'm interested in.
Fantastic. And what kind of modalities of images have you been working with?
It's bright field and fluorescence microscopy images across 25 different structures.
Great. Cool. Are they brain images? Brain images?
No, these are human-induced pluripotent stem cell images. So the single cell level, also FOV level.
Great. Cool. Very cool. It was nice to meet you all. And hopefully we'll stay in touch here. Feel free to make extensive use of the Slack throughout the week. And I'm not on the Gather Town. I don't know, has anyone else tried the Gather Town yet?
Yes.
How did it work for you?
I find the whole thing kind of amusing.
So I tried it for a while, but I couldn't find the HUD for our tutorial. So after running around for a while, I gave up.
I think it is a game and it's supposed to be amusing, so maybe it's achieving its goals. Okay, so let's step into web visualization next. We can get started. It sounds like a couple folks, many folks are probably interested in this topic too. And so this topic in this section, we're going to go into the different browser rendering technologies and how they work, their capabilities, and their limitations. Specifically, we're talking about the ImageJ element, the Canvas element, WebGL, WebAssembly, and WebGPU. Then we're going to talk about trade-offs between server-side and client-side rendering. And then we're just going to introduce some projects, non-comprehensive list, but a few example projects that I'm involved in that might be of interest to you. So starting with browser rendering technologies, we're going to start with the basics, which are these ImageJ elements, which is an HTML element type that allows us to embed an image in the web page. And these have been around since the dawn of the internet. They're supported by all browsers. They support formats such as PNG and JPEGs. More recently, WebP, AVIF, APNG. You can also inline support in a base 64 encoded image. So you don't have to have a separate file, is what that means. Great support, very simple, nice to work with when you do need it. The limitations are that it's not well suited for dynamic content. If you want to interact with it, it can be difficult. And when we're doing bioimaging and working with microscope images, we'll often have pixel types that are floating point numbers or multi-component pixels, or we'll have anisotropic spacing in how the pixels are sampled, especially if it's 3D or meta 3D images. And this does not support that. You can run this cell in Jupyter and IPython. You can output HTML and just view that directly in the notebook. So here's the image source element. Any comments or questions on the ImageJ element? Okay, let's move on to some more interesting and exotic tools. The Canvas element. So the Canvas element is a different type of HTML element, but it's capable of drawing 2D graphics and 3D graphics, as we'll see next. This is, again, supported by all browsers, and it's better suited for dynamic content. There's a low-level APIs that can be used, or there's high-level JavaScript libraries that can also be used with it. Again, to interact with the canvas, we're going to use the JavaScript language. It does have limitations for our needs. Specifically, if we want to do 3D imaging, it's limited. And relative to the WebGL and WebGPU technologies, the performance is limited in terms of using the GPU. So here is an example. And this is JavaScript code. We are going to first create this HTML element with JavaScript and get what they call the rendering context, so something that you can draw onto from the element. And that's called context. And then there's an API where you can do things like draw lines or fill rectangles. So we're going to put a green rectangle with these dimensions, specify these dimensions into that canvas. And this at the end here, this is something specific to Jupyter. So Jupyter has a kind of global variable called element. That's the output of the current cell, the DOM element, and we can append that canvas element to it. And we have a green rectangle. To move on to something more exciting is WebGL, which provides us the fancy 3D graphics accelerated on your GPU. And this is a technology that's a web standard. It's available across all browsers now, all major browsers. It provides hardware accelerated 2D and 3D graphic support, but it also draws on this canvas element. So you interact when you're programming it with JavaScript APIs on a canvas element. It's available everywhere. It has widespread support, great performance. There's a low-level API. There are JavaScript libraries available for scientific imaging. Kitware, the company I work with, it develops V2K.js, which is a library used for scientific imaging. There's also 3GS is another common library that's used. And we can do the 3D support. The limitations are resource limitations. So we can't add an arbitrary large volume to be rendered because of limitations in the browser. So maybe once you get beyond maybe a gigabyte of data, you run into issues. It's also using APIs that are using an older standard. And there's a new standard that is maturing called WebGPU that is sort of a more advanced API that works better with GPUs that's coming out that might be replacing this. So here is an example. And this is using a library that I helped develop called I2K widgets. It's working in Jupyter. And this supports the 3D visualization with WebGL. It's interactive, so you can very easily interact with the scene. It's volume rendering. Very important for this kind of registration idea and multi-scale idea is that everything's put in the screen, in the scene, in a physical space, and you have physical dimensions in the scene. There are interactive controls to control the rendering properties. And you can do 2D and 3D slice views. See, it's very interactive and good performance. I can inspect the data and probe the data. So this is somewhat similar to like Vizar. I'm not too familiar with Vizar. It's relatively new. This is a little older. We're working to also add support for ZAR and these multi-scale data sets. There's work in progress to make that happen for this rendering tool. I2K widgets is the Jupyter widget interface, but there's also a standalone JavaScript library that this is based on called I2K V2K Viewer. And then the final technology to be aware of is WebGPU. And this is different from WebGL. It's the working name for the future web standard that is in progress. All the major browser vendors and the major operating systems are working to support it. That provides a JavaScript API for accelerated graphics and compute. This is modern graphics. And what that means is kind of with WebAssembly, where we had this standard assembly code for CPU computing. This is kind of a similar thing. It supports it for GPU computing though. And it's the next generation, but it's not completely standardized yet. It's hidden behind flags in the browsers as of today, and they're building consensus on it. It's not yet broadly available, so we don't have an example. Are there any questions or comments on the rendering technologies in the browser? So these web standards, another item I forgot to mention is that if you want to see what is supported by the different browsers, there's a great website called Can I Use? And we can see, for example, any web standard. Let's see, web GPU, you can search for that, and it'll give us the status across all the major browsers and operating systems, mobile and desktop, what versions they have it, to what degree they support the standard. So here we see web GPU isn't quite supported yet. It's not finished. Go to WebGL. We can see that it's supported by most browsers, short description. And then you also get an idea of the market share of the different browsers, how many of them support it. So in this case, of what's actually used, 98% of potential users do have support for this technology. So we kind of hinted that there are maybe two broad categories of visualization and rendering techniques. One is server-side rendering, where data is rendered on the server, and a kind of essentially a screenshot, a JPEG is created from the rendering of the scene, and that's transferred over the network to the client and then displayed in the client. The other type of rendering is where rendering happens on the client in the browser. So the underlying data is sent. That might be the samples from the microscope, and that data is sent in some form from the server to the client. There might not be any explicit compute server available at all. It might be just something that's providing data, or resource that's providing data. And there also might be maybe a server that does dynamic generation of a multi-scale pyramid at the same time. So you're not providing the entire data if it's a very large imaging data set. And in that case, the image is generated on the client. And there are trade-offs. There are trade-offs as with many computational situations, and advantages to each approach. The advantage, what's the advantage to server-side rendering? What are the advantages? In server-side rendering, you know the GPU that is being used to perform the rendering. And because you know its capabilities, and you can provide a beefy, large GPU that's always sufficiently powered, even if it's being viewed in something that may be underpowered, like a phone or a very weak laptop. And for these large data sets, sometimes maybe we want to have a GPU with more memory capacity. Or we might want to support other capabilities, rendering capabilities that aren't available in the web standards yet, like ray tracing. And so we can do different type of rendering, possibly. There's a shorter technology path. There's less work required. If you have a traditional desktop application, you want to make it available on the web. Server-side rendering, instead of rewriting the entire software, is easier in many cases. And we don't need to transfer the raw data to the client. So sometimes this can be faster, sometimes it's slower. The difference is determined by how much data needs to be sent and how much interaction you're going to have with the data. So if you're continually rendering and interacting with the data, you'll always be sending screenshots. And in that case, it may require more network transfer. Typically with the client-side rendering, we need to be very intentional and specific in how we send the data and what data we send. So we may reduce the data in some way, and we may compress the data, and that can reduce the amount of data that's sent over the network. The performance and responsiveness for client-side rendering is generally better. And that's because we have the data, it's on the client. Maybe we rotate that data set, we interact with it, we interact with it in some way, select in a zoom level, and that interaction doesn't need to go all the way back to a server and the server respond to it, create a new rendered image, and send that rendered image all the way back to the client. So the loop is much tighter, which results in better performance. It's also much easier to maintain and simpler, which reduces costs and just the burden of keeping the system running. So it can be a challenge sometimes to get the server-side software set up and also to make sure that you have a GPU on the server. And of course, that GPU, if you have more than one user, it can be overloaded by multiple users. Any questions regarding server-side versus client-side rendering? Comments? Oh, so what are some example tools that you can use that are open source and work for these bioimages? For server-side rendering, PairView Web is a server-side rendering tool that uses PairView, large scientific data application for rendering server-side. It might be installed on many of your clusters, or VTK, the visualization toolkit. And it'll render it on the client with those tools and then send it to your web browser. You can click on some of these applications to try them out. Another example are a few tools that are desktop tools, but they have some support for use in Jupyter, limited Jupyter support. There's some interaction and performance limitations, but Napari is a multidimensional viewer for Python. 3D Slicer is another project that I'm involved in that has many capabilities for image processing and three-dimensional visualization. In terms of client-side rendering, there is Vizar, which was mentioned by Anders earlier, supporting this ZAR data storage system we'll talk about next. Another is I2K B2K Viewer. That's the foundation for the I2K widget that we saw before. Another interesting project is ImageJ.js. So what is that? That is the traditional Java application, or Fiji, that you've used on your desktop, but it's been compiled into this WebAssembly technology we discussed earlier. And so it can run directly in your web browser. Also means it can run anywhere in any standard web browser. and without installation. So this combines WebAssembly with this ImageJ technology that we're going to be talking about in the future. Other interesting applications, Kaibu, which is kind of like Napari, but a pure web implementation, bringing together visualization and annotation capabilities, client side. One of the oldest and most widespread applications is called NeuroGlancer. It came out of Google. It's used in the neuroscience community, but in also other communities for these very large data sets, 3D data sets, and it's a WebGL-based viewer for large volumetric data. And another project worth mentioning, because it's another I2K tutorial, is this WebKnosis. Check out that tutorial if you have a chance. And then some systems support both client-side or server-side rendering, like Matplotlib, the de facto Python visualization library. And I'm working hard to add flexible rendering backends, like with Matplotlib, to I2K, V2K viewer, and the I2K widgets. You can do server-side rendering there too. So this next example allows you to run ImageJ in your web browser. This is using an iframe, and it looks very familiar. And what's exciting here is this is using all web technologies. And here's another example with I2K, V2K viewer running outside of Jupyter for cell data set.
So to use something like this, how do you store the data? And maybe this will be the whole next, other than the example data, how do you get your data into it?
It's a very good question. And there are many paths, and the different paths have different capabilities. And for this example, here we're just providing in the URL, we're providing a link to the data. So we put a link to, if you have any data set, like a PNG, if you put a link there, it's going to download that data and load it. There's actually some support for ZAR here too. And that's sort of a lazy loading of the data set and capable of multi-scale visualization of the data sets. So working on that capability more and more, you can see there's capabilities to select regions of interest in the data set. So kind of where it's going is you'd be able to select a region of interest on one of these multi-scale ZAR data sets, for example, and then it'll lazily load a high resolution version of that region of interest. That's kind of what the concept in NeuroGlancer and Big Data Viewer, if you're familiar with the desktop ImageJ or Java application. So that's coming with just kind of HTTP. You can also, so if you take this and remove the file to load and just get the app, then you're presented with this blank page, but you can just click on it and then you can select a file that's on your local computer.
Okay.
And yeah, so then it's going to take that and actually load any of the data sets that you have as using WebAssembly. So the reader is written in C++ and load the data that way, and then it passes it to this WebGL rendering.
That's nice.
So those are the options now, yeah. So explore, it's really fun to explore with these visualization tools and get to understand them. Try it out, try these out, try it out on your own data sets. This viewer. Another way to kind of understand what's happening is this exercise. So in this exercise, let's look at Matplotlib and look at the different rendering backends we have to use and the ones that work in the notebook in the web browser, and see if we can figure out what is the technology that it's using on the browser side. So what we can try here is, these are the different kind of rendering backends that are relevant for the notebook. We can, if you run this cell, and hopefully, does everyone know how to run Jupyter Notebook cells? Yes, I'm assuming yes. If not, feel free to speak up for any of these issues. But Shift Enter to run the cell. And you'll see the output below. And let's, here, this is interactive, and there's something happening in terms of the technology here. Let's use our new debugger superpowers and open up the console and inspect the output that's generated. So using our element inspector tool on the left, you can click on the rendered part of the data set and see if you can see and understand what are the different rendering technologies that are used client side for these different Matplotlib backends. Every time you want to change a backend, you have to actually restart the kernel. So you do that because it can't switch dynamically. But we take 5 minutes and try changing some of these backends and look at what the output looks like and try to interact with it, see what that looks like, and look at the HTML that's generated. right, so what did folks find? What type of elements were used for the different rendering backends? For the inline backend, Simon, what was the rendering method used here? Were you able to find that? So for this method here, we had this IMG. So it generates an IMG on the server, and then it sends it to the client, and it sends it actually as a base 64 encoded image. You see all these characters. It's just the data is converted to this base 64 encoding as a PNG, and that's how it's sent. We can try some other method like the IPyMPL backend. And in this case, if we use our tool to look at the element, it's a canvas element. And you see when we're using the canvas, it does kind of some rendering and a conversion of this data that is floating point data into something. Matplotlib will do something that changes it into unsigned short data before sending it to the canvas. But the canvas does have some interactive rendering capabilities to it that you don't have with the static IMG. So you can move it around and render it in different locations. Did people have any questions that came up as they're exploring this, or any other thoughts, questions? All right, so let's get ready for the next section, which is image data storage. We'll take a 5-minute break. And when we come back, we'll talk more about the czar that was mentioned before, N5, standards in our community for microscopy and working with these large images, and how that helps us work with storage that are the storage systems of the modern cloud. So let's reconvene in 5 minutes. All right, friends, let's talk about data storage and the web. Everyone's ready? So in this section, let's talk about data storage and how that works with cloud storage systems. And let's also get some experience with ZAR and N5 and understand how they work and why they work the way they do, and understand the relationship between these chunked and compressed object storage formats and how that helps us for parallel processing of the images and multi-scale visualization. There is another tutorial going on this week that was created by one of the lead authors of these new standards, who's organizing the standard, Josh Moore. And take a look at that if you're interested in this topic. That should be more comprehensive tutorial. But let's briefly go over kind of these technologies, the background behind them, and what they mean for us, why they are the way they are, and how they also fit with the web technologies that we've been discussing so far, and also the distributed computation that we're going to be looking at next. There are just a few basic concepts, but they're important concepts. And once you get them, it'll make sense and as to why these are really important and why they're relevant to what you're trying to do. You'll see referenced, if you're looking for cloud storage services, like you'll see AWS S3, which is Amazon's cloud storage service, the most popular storage. And you'll see Google Cloud Storage and Microsoft Azure Storage, other cloud storage service providers. And there's also similar types of storage services, APIs that you can provide with your own open source implementations that you may host in-house, the Minio Cloud Storage service. The way they store data and provide data and interface with data is different from what we're used to with our traditional file system storage. So in file storage, we have files and folders, and we organize data that way. And these files and folders are generally stored in a pool of storage, maybe a volume, a drive, and that drive has a limited capacity, and we read and write files on that file system. Data inside a file can be overwritten. Parts of a file can be overwritten. And the metadata associated with files is limited. We might have a timestamp and a file name, but it's relatively limited. When we start looking to the cloud, these are what they call object storage systems, S3, Google Cloud Storage, etc. And in this case, we have objects, and these are binary blobs. So the equivalent to a binary file, but it's living in a flat structure, a big pool. And these binary blobs have unique identifiers, hashes associated with them. And they also have some metadata associated with them. So this metadata format is JSON compatible. And JSON is the JavaScript object notation. So it's a data format that's associated with JavaScript. So that format is JavaScript friendly, which means it's web friendly. And it works very well with all the tooling that surrounds the web. And these object storage systems are also very well suited for access with simple HTTP requests. The difference between them, though, is that they cannot be modified in place like you can a file. So if you want to create a new version of an object, you need to create an entirely new object because it's hash rate change. But it has the advantages that you don't have like a finite drive, and once you run out of space, you have to get more drives or recreate a volume. You can grow it with these services, these abstractions, as large as you need, and generally you only pay for the storage that you use. So those are kind of some of the advantages. The other advantages is that it's very well suited for parallel computing, as we'll see next. That's how cloud storage works in general. Any questions about cloud storage, object storage versus file storage? Okay, so we have this new object storage world that we live in. It's a little bit different from our comfortable files and folders. And we want to use that for imaging. And that's where ZAR and N5 come along. And these are file formats that map well natively to these object storage services. They also have some characteristics that make them suitable for storage of large bioimages. So together, were sort of developed in parallel by people coming to the same conclusions, but now they've sort of started to work together as a community, and these ideas are going into a standard, the next generation files format that Josh Moore is working on, and others, to be a standard of how we store imaging data, scientific imaging data in the future. And essentially, this is a hierarchy of n-dimensional dense arrays with metadata. So both these formats support this idea of kind of a hierarchy of data. So HDF5, if you've heard of that, kind of the same concepts and capabilities as HDF5, where you have things organized in the equivalent to folders, and then you have these binary data sets within them. Within each one of these hierarchies, you can have JSON compatible metadata. So then that just maps very nicely to the object storage systems. And you can also have these chunked n-dimensional binary tensor data sets. That allows us to store parts of an image in a chunk, also compress that chunk so it's reduced in size, and retain the n-dimensional characteristics. So what is the different dimensions of the image? What are the different dimensions of the image? And when we need to load that data, we have to load an entire chunk, an entire object at one time. But since that object is not the entire data set, we can just incrementally load the parts of the data that we need. And before we even load it, we can get the metadata that describes the data set, so we can learn about how large is the data, how large is the image, what is the pixel type of the different pixels in the image, etc. And for these binary tensors, these n-dimensional tensors, we support the basic component channel pixel types of 32-bit floats. So not just these 8-bit integers that are common with PNGs, etc. In addition to that, these new file formats also support new compression codecs that are faster and have a much higher compression ratio than previous compression algorithms, which is helpful. And in practice, it makes a very large difference in the size of the data that needs to be stored and how fast it can be transferred on the network. So that's the format that describes how the data is stored. And we combine that with a model of how we represent a scientific image in this format. And that gives us OMI-ZAR, so the Open Microscopy Environment ZAR format, which is under standardization. And that helps us visualize large images because it's a multi-scale format. It'll have pre-computed multi-scale image pyramids that can be helpful for large image visualization. The other property of this object storage model is we have these chunks of the image, and that is very helpful when we want to write and create compressed chunks in parallel. So when we go to write a compressed chunk, before we create it, we don't know necessarily how large it will be when it's compressed. So since we have these separate object blobs, and then it's not just one large file that needs to be contiguous, this is helpful for very helpful for parallel computing. I know we were discussing things like registration and metadata. So another image model to be aware of that works with these file formats, ZAR in particular, is Xarray. So it's not listed in the notebook here, but we should go over it. So Xarray is used by the climate science and geoscience communities. If you're familiar with Python and NumPy, you have these n-dimensional NumPy arrays, but this adds to that metadata, particularly naming what the dimensions are, X, Y, Z, T, for example, time, the different spatial dimensions, and also metadata like what is the spacing between pixels, which is often different, and where is the origin of the image. So that adds that, and Xarray also supports serialization and deserialization from ZAR. So this is another kind of data model that can be used. It also has very good support for DAS, which we're going to talk about next for distributed computing. Any questions?
Question, yes. So you mentioned AWS S3 and ZAR. So each of the different ZAR image parts is stored as a separate S3 object. Is that so? Like a ZAR image may consist of like a few thousand of these separate multi-scale images, and they're each stored as a separate S3 object. Is that correct?
Yes. So each chunk is stored as a separate object of the image.
Do you have any experience with performance of that? Does it work well? Does it not work so well? Or no idea?
It works quite well. So what it enables is that you can fetch the different chunks in parallel on the network. That's one of the things it helps with.
Okay.
So that's kind of one of the things it helps with. And then you can fetch just these smaller chunks instead of the entire volume, which is in practice essential.
Okay, thanks.
Good question. Any other questions? So this is really kind of cool and interesting technologies. And one of the things that makes it so cool is it's simple, relatively simple, and easy to understand. So it comes down to files and folders and JSON. If you're not familiar with JSON, it is this way of representing basic data structures. So this next exercise, we are going to actually download one of these ZAR images in this new OMIZAR spec with the OMIZAR library. And we're gonna just get the metadata from it. And then we're actually gonna download the entire image, compare how long that takes to get the metadata versus getting the entire image. And that will download to your file system, and it's going to be a group of files and folders. So kind of the default storage is this file system storage. It is files and folders. And we're going to examine the layout and the content of the files. So there's some commands here to list the folder contents and read the contents of the files, and then list the folder contents here. So see if you can look at the content of the files and get an idea of how this format works, how it's organized, where things are stored. And then we'll open it with the ZAR library and look at the metadata, look at the data itself. When you look at the interface in the ZAR library, one thing to notice and keep an eye out is that things are lazy. So this idea of laziness means that we can get metadata, a description of the data, but we don't actually get the data itself, the bulk data, the pixels, the pixel data, until we do an operation that requires us to actually read that data, which is important for very large images when we don't want to run out of memory and parallel computation. So most of the commands are here. You want to run them and take a look at them. This was the notebook that had some issues in the last session. So some folks, when they ran this command, it put this folder inside this folder. And I tried to update the commands here, but if you have issues, just speak up and we'll see if we can get them resolved. So let's take 5 minutes and see if we can understand how ZAR works. All right, hopefully you had a chance to probe some of this data, inspect it a little bit. And we can see this data set is a multi-dimensional data set where one scale of the image, it's in this folder 0, and the second scale is in the folder 1. In the metadata is stored, when it's stored on the file system, as separate files, .zetters by convention, and .zgroup, and PyCat prints the content of a file. So we open that up and we see that it's a plain text file with JSON format having the metadata, and the metadata is specific to this OMEZAR. So there's keys like multiscales, and the data sets of those multiscales are in path 0 and path 1. And then there's some other metadata that's related to the window and level and color maps that are used on the data. There's a Z group metadata file. This just has format identifier, version number. And then when we look in one of the groups or paths, depending on the naming convention you're used to, we see there's lots of files. And each one of these files is a binary file that corresponds to a chunk in the data set of this multi-dimensional array. And each chunk identifier, the dimension is separated by a dot. And there's 5 dimensions. And for OMEZAR, that means the dimensions are time, channel, XYZ or Z by X. I have to look again to get that order. It's important. And those are the identifiers for each chunk. And each one of these files is compressed. There's also a .zarray metadata file that's there with the array. And if we look at the content of that file, what do we see? Having an issue there. I think this is wrong. Should be that 0 is in the wrong place if you had an error on that cell. This is metadata in JSON format that describes the multidimensional array. So we see how many chunks are in the array, 1 time, 1 channel, 1 Z chunk, and then there's 275 chunks. We see information about the compression codec identifiers and the shape of the array once it's been uncompressed. So any comments or questions or thoughts there on how ZAR is stored? So this is the kind of, they call this the file system storage backend. We can read that by just putting the path to the folder. ZAR also supports taking all this folder hierarchy and files and zipping it into a single zip file and then reading the file that way. So if you want to transfer this image around by zipping it into a single file, that makes it less cumbersome to transfer around. It also helps the performance when you're transferring from file system to file system, as opposed to objects cloud store to cloud store. Because the file systems, when there's lots and lots of these small files, some file systems are challenged by that. performance-wise. So you can open a zip file in that case, or you can point this to an HTTP URL, or it can have backends for direct access to some of these S3 and other cloud storage systems. So the library, let's open it. Loads very quickly because it's not actually loading the data. And we can get the metadata directly that describes the data set. And then we can get metadata about the image pixels, the bulk data itself. And that loads very quickly. But we see that the type of that data is this ZAR array, which is this lazy array. And we know the shape of the data and the type of the data, but we don't have to read the actual data, pixel data itself, to learn about that data set. If we want to process it as a NumPy array, then when we run this cell, it takes a little longer, and it's actually going to load the data from the disk and provide us the values. Those are the basic concepts of data storage. Any questions on these next generation data storage formats? All right. So our next section will be distributed image processing in the cloud. And this is going to bring together ZAR and chunked compressed data storage with some of the HTTP and web technologies we've talked about. And in this next section, you're going to create your own cloud cluster dynamically here. If you have some time during the break, you will need a coil.io account. So you can go to coil.io, try coiled, and then you can log in with a GitHub account. If you don't have a GitHub account, you can create one. And you'll need an account to get started. This is a new service, and we see kind of prospective costs, but they're in a beta state, and the service is free for now. So you won't need to pay anything or use a credit card. So let's reconvene in another 10 minutes. Let's do 10 minutes, 10-minute break at 4:02. right, we are getting to the next section on distributed image processing in the cloud. It's an engineering heavy section, but I think a fun topic because you get to create your very own cluster just for you in the cloud. I don't know how many people are familiar with Dask. We're going to be using Dask in this section. And if you're not familiar with Dask, you'll get the basics and you'll be able to use it by the end of this section. So we'll get some interaction with Dask for imaging. It's used for other types of scientific processing, but we'll use it for imaging. Then we're going to actually create our Dask cloud cluster. And we're going to discuss and experience some of the details of making this work. And that detail is making sure that we have a consistent software environment across all the different resources that are running when we do distributed computing. Is anyone here familiar with Dask? Has anyone used it before? No? Sarah, no? Anybody else? No? Okay, great. So Dask is a distributed computing library for Python. And I think if you've heard of MPI or these kind of Condor cluster computing libraries for distributed computing, you had to do a lot of low-level programming to make them work. Kind of the promise of Dask is to provide flexible parallel computing either on your local system workstation or on other types of distributed computing environments. Like maybe you have a couple computers in your lab and they're connected via the network, or you have access to a university or national lab HPC cluster, or maybe you have access to a cloud cluster. And it abstracts that all away from you, and it allows you to develop using libraries that have Python interfaces and use the same code that you maybe develop on your local machine, then run it on a very large data set with these distributed computing resources. That's the idea. And how does that work? So it comes with these special collections, these data structures that are split into smaller pieces, components, that allows it to create task graphs from these pieces to process the different tasks. So you can have a Dask array, and that's primarily what we're interested in. It's a multi-dimensional array, but it's split up into different chunks. And we operate on that task graph to create a directed acyclic graph, a graph of tasks, and that puts that together, that graph. And then Dask provides a scheduler. That's kind of one of the main things that it provides. So it creates a heuristic and set of rules for distributing all these different tasks represented by a shape here in this diagram to the different machines or the different processes or different threads on your machine running on different cores. And so it can run on your single machine on multiple threads or cores, or it can run in these more distributed computing contexts. So it was originally used in Python because Python doesn't has a harder time with parallel computing just on a single machine, but it can also be used for distributing computation for very large data sets on clusters. That's Dask in a nutshell. Any questions about that? It'll be a little clearer once we start to use it and we can actually see how it works, what's happening. So going back to the last lesson, let's load again the same data set, the same multi-scale image data set that we had stored in ZAR on the network, the UK in the UK on S3, but we're going to access it through HTTPS this time, so directly through the network. We're going to open it, and we're going to look at the lowest scale from the multi-scale image. And we're not just going to load it into a ZAR array, but we're going to load it into this Dask array. And then we're going to look at what it looks like. So that happened very quickly. And it's a larger data set of 70 megabytes. But we only loaded the metadata. So we can get the structure of the data and understand the basic structure of the data. This Jupyter representation gives us a little more information about the structure of the data. So the entire data set is 70 megabytes, but each one of the chunks are 150 kilobytes. And the multidimensional array has these dimensions for the entire data set, and these dimensions for a chunk. And that's visually represented on the right here. The entire data set's shape is 236 by 271 by 275. And then each one of these chunks, it's a 2D image is a chunk in this case. It doesn't have to be that way, but in this case it is. So you can think of it like a stack of images that comprise the whole data set. Then we have this tasks and chunks. So going back to this task graph, we can think if we want to process this data, and then in this case, it just means to load the data. We have 473 tasks to load the 472 chunks. Makes sense? And the type of the pixels is an unsigned 2-byte integer, and each chunk is an ND array, an NumPy ND array. Okay. So this is a Dask array, but it has a lot of the interface, the same interface as NumPy arrays. Very closely mimics it. And we can do things like slicing on it. And so let's extract from this data set that has one time point and two channels or two components, the first channel. So we're going to take the first time point and the first channel and just get a single volume, 3D volume. Now that volume has half of the original data set from 2 to 1. There's increased tasks to generate that volume. So we're going to have to just load the data, but then also do some work to extract the single channel. And same other metadata. Okay, now let's use I2K widgets to visualize that data. So run this cell. And this time it's taking longer. Why is it taking longer? It is because it had to actually load the data in this case. If we want to visualize it client-side in the web browser, we need to load the data from the HTTP resource and send it to the browser so we can render it. So it takes a little bit longer. And then once we have the data in the browser, interaction is very quick and responsive. Okay, any questions about the Dask array interface to the ZAR dataset? So this is just loading the data. Let's try to do some computation on the data set. Let's say we want to downsample the data set. And with Dask, you can run Python functions on the chunks. You can have common image processing schemes like run a Python function on a expanded version of a chunk and then throw out the overlapping regions and use the trimmed result. So you can think of convolution if you wanted to do convolution operations and get the same result on a chunked distributed computation as non-distributed computation. That's a way to do that. So in this case, we're going to just run this function called coarsen. And this takes in the function that you're going to run that's going to reduce the size of a chunk, the Dask array that you're going to run it on, and then the reduced size that you expect in every dimension. So we're going to reduce the size by 4, and we're going to run mean in this 4x4x4 local grid. And then we have this option at the end that says trim excess. So where this doesn't factor cleanly into the chunks, we're just going to throw away those results and remove them. So we can call that, and it's going to return the metadata of the structure that would be computed if we wanted to compute it. So, but it doesn't actually compute it again. So in this case, 2 megabytes instead of 70 is the result. This shape has changed. It's smaller. There's many more tasks. The type has changed to floating point data. And the computation is lazy. That allows us to go from ZAR to ZAR without loading all the data in memory, is really what that allows us to do for a giant image that might not fit into memory. But if we want to load the data into memory, we can say do that by calling compute on the Dask array. So run that, and let's see how long that will take. Okay, 3 seconds on my system, which is pretty new. Your mileage may vary. Get an idea of how long that took. And what is the type of this result? What does that return to us? It is not a Dask array, but a NumPy array. And the shape has changed. And if you look at the content has changed too here. Okay, any questions about that, the lazy computation? All right, now when we did this computation, we did it locally on our system that's running this Jupyter kernel. And we did it serially, so just not in parallel. Now let's create a cluster in the cloud, have fun engineering, and run it in a distributed way for the different chunks that comprise the image in the cloud. So if you already logged on to Coil, created an account in Coil, you'll need that for this next step. So here we're going to import the Coil library, and then running this. I've run it before on my local system here, but you probably have not. And so you will get a prompt on the output that says, return to me the token that identifies your account and save it locally so that we can talk to your cluster. So if you get that, go over to coil.io, and in the upper right, go to your profile. Then and click on the eyeball to see the actual value and copy the actual value. And go back to the notebook and paste it in for the token. So it'll set up your account. And you can save the configuration and prompt you to save it locally, say yes. And then it will start with the cluster for you. So it's going to spawn this cluster. It might take a few minutes. So go through those steps. And then once you get it started, click on this dashboard and you can kind of see the status of the clusters that you've started in the past. I have pending clusters here. And it'll go from pending to running once it's up and ready. Next to the running, there's an eyeball that says View Dashboard. You can either click on that link or back in the notebook, you can click on the link provided below. And that provides a dashboard to the scheduler. So visualization of what's happening, what's seen by the scheduler. Right now, we're not running anything, so we don't see anything. But as things run, there's different tabs here, and you can keep track of how many different workers you have, what is their CPU usage, memory usage, what are the tasks that they are running. The tasks will get names, and overall status of the system. And back at the dashboard, you'll see what it would cost if you're paying for this, the total cost and the cost per hour. This is free for now, as the service is new. How many workers you have, the software configuration you have, the cluster configuration, and the cluster name. If you wanted to reuse the cluster, instead of spawning a new one, you can go back and put that as the name parameter as a string here, and it'll reuse the cluster. You might get this warning, mismatched versions, and this is kind of the real world gotcha that you have to watch out for. It's important to have the same software on everything that's running here. So we have software running on our computer locally, and it has packages installed in it. And then we have the software that's running on these workers on the machines in the cloud, and the software that's running on the scheduler. And they all should have the same packages installed with the same versions. And we do that by using this conda environment and the package version specified there. And there's documentation on how to create a consistent software environment. That's what this argument is. So who has their cluster running? Yes, thumbs up. Great. Awesome. Andres too. Cool. Does anyone not have their cluster running who's still with us? Okay, so let's go ahead and run the computation again. But we have our cluster running, and there's kind of this global configuration for Dask. And if the client has been registered, it's going to use those resources. So let's run it again. This next cell, the same call, but take a look at our dashboard. Let's try this again. I am not seeing, so you should see in the dashboard some activity here of tasks and task processing. Let's take a look again. I'm going to restart the client. Using the existing cluster and run again. Is anyone getting different output in the dashboard? This was working earlier. I'm sure. But live demo. So if it is running on the cloud cluster, you should see a bunch of colors as tasks start up in that task graph and which different worker is running at a given point in time. You can also run a local cluster on your local system just by using threads or processes and run again in that case. This is what you should be seeing on the cloud cluster. If it's running on the cloud cluster, I'm not sure why it's not running for me, but it looks like this one is running on the cloud cluster too. And it's using, these are different tasks that are running. You'll see the data that's transferred and the tasks that are queued in the system as it runs. So let's take 5 minutes to kind of play with that, explore that. See what are the different timings for running single-threaded locally. We did up here. Running multi-threaded locally with this local cluster. And then running in the cloud cluster. And after you finish with that, you can also change the data chunk size. There's different factors that affect the performance that we achieve. One of them is the network connection. One of them is how large are the data chunks that are sent to in a task. So if a data chunk is too large, then it'll take too long to run on the worker. But if it's too small, it will compute quickly on the worker and it'll spend more time transferring the data than it does actually number crunching on the worker. So there's this optimal chunk size for the data, and that depends on the problem that you're working on, the type of computation that you're doing. So something that you may need to be optimized. If you want to change the chunk size, there is a rechunk function. So we can say rechunk is on the task array rechunk, and Here we can specify a chunk size. Before it was this size, we can change that. Okay. Friends, what did you find? What works best for you?
The cloud cluster was actually the fastest for me.
Oh, it was. What was the speed difference?
All of my times were really slow compared to what was already in the exercises, but it was 11.5 seconds on the cloud, 14 seconds on the local cluster, and 83 seconds on just my regular CPU.
Wow, and so where are you located in the world?
San Diego.
Okay, and do you have a fast network connection or not?
Not particularly, especially when I'm currently downloading data and my husband's also on Zoom and there's just a lot going on.
Okay, yeah. Sounds like that made a difference. That's really interesting. Any other results?
I had the same results. So it took 28 seconds to just compute it locally on my machine. 14 seconds using the cloud and 18 seconds using the local one.
Wow, that's really interesting. So yeah, my results were quite different. So I get faster results locally, much faster results locally. Any other experiences? So as you can surmise from this experiment, it's going to depend a lot on where the data is located, how fast are the network connections. In this case, it may help to some degree. For larger data sets, of course, it's going to help a lot more. You can also scale the size of your cluster here to help work with larger data sets. So this is a relatively small data set. And the operation we're doing is relatively simple. Just a mean, a local mean. So I think as you're doing more complex operations, this type of distributed computing may pay off in more contexts. If anyone tried the chunking, so here's an experiment with changing the chunk size from how it was stored natively and increasing the chunk size. So before we just had one slice and I changed it from 1 to 64. So it's a larger chunk. And that even for this, so for this simple operation, that seemed to improve performance consistently. So that was faster when we had larger chunks versus the default chunk size of how the data was stored on disk, which is common. So a strategy that you often want to use is to use as large chunk size as possible without running out of memory or without the worker's communication timeouts. So that reduces the amount of overhead of scheduling and doing network transfer of the data. Any other thoughts or questions or ideas on Dask or cloud computing? All right, so let's proceed to the last section, which is on reusable components for web-based image analysis and visualization. And let's try to finish by 5 o'clock, 20 minutes. And this is a short tutorial, short section that presents this new library system called ImageJ, so joyful imaging, which is what we're going for. There's also another tutorial by the author of this program at I2K 2020. Take a look at that, or sign up for that if you can, or participate if you can. This is just kind of a very high level overview, but it's such an important new library that fits in with everything we've discussed. Open, reproducible, easy to use programs for the web, that it's good to try to have an understanding of what it is and how you can use it. There's this diagram here that looks a little complicated, but in a nutshell, you have these plugins. It's a plugin framework that lets you run plugins, think ImageJ plugins, that might do some processing or some visualizations and compose them together. But the difference with ImageJ is that these plugins are either client-side running in JavaScript or server-side running in Python. And you can combine them together. And so kind of what does this mean in practice? So this image down at the bottom, you can click on it. It has a link in it. And it will open up this web app. And this is the default front-end web app. And we have in the URL a path to one of the default plugins. And this is a skin lesion analyzer running a deep learning model to assess whether a skin lesion is cancerous or not. And it's running in JavaScript. We can install it into our workspace, which is basically this web page here. And once it's installed, you see it listed on the right, click on it. Gives us a warning. And so, and it loaded some default data. You can move this around in this workspace. But you can load your own data set into this and then click predict, and it runs the image analysis deep learning pipeline, gives us a prediction that this is probably a melanocytic nevi. And that displays the results. So that's kind of concretely what this can do for us. And then we can combine this with other plugins. We can add new plugins here. There's many that are shareable. And we can also create our own custom front end. So if you wanted to create a custom application with its own front end without all this stuff, you can do that and share that with another biologist or someone that you're working with who's not very technical. And then they can, they don't have to install anything, and they can do some really powerful analysis of their images. Let's see. And so what is the anatomy of these plugins? They can be written in Python, and here's a basic one, or JavaScript. And this is what a JavaScript one would look like. This is a hello world one. So these plugins have a setup function that optionally can do something to set up the plugin, and then a run function that executes. And you can add plugins to this workspace, and then they can communicate with each other and use each other and call each other. And they can be either running server-side or client-side. So this one runs the I2K viewer. It provides an interface to that, so you can combine it with other things in this environment. Or you can write a JavaScript plugin in JavaScript. And here we're writing in JavaScript and then running it, adding it in Python. This is a Hello World plugin. So we can change the content here. Hello World, and then it changes the message. And this is just something to be aware of, but there are a lot of examples out there. It's great for reproducibility and to reuse some tools and to kind of combine them together to do new things, new interesting things. There are all these examples that you can try. Are there any questions about ImageJ? So take a look. You can search through the default repository of plugins. You can create and publish your own plugins depending on the type of research that you're involved in or you're interested in. You might find something interesting there. And kind of as homework, you can play around with that more. So that concludes our tutorial. I hope you found it was helpful. You learned something. If you have any feedback, ideas on what was really helpful, what you got a lot out of, what you didn't get out a lot of, what you'd like to see more of, I'd really welcome that feedback. If you want to keep working through these tutorials and have other ideas, be on the Slack through the next week or the Gather. I'll get on the Gather later in the week. And if you have ideas with some of your peers, if you want to work on some projects together, that's also a topic to pursue further. But thanks all for working through this long tutorial. I know it was a long
Rotating at 6.
tutorial, but hopefully you found it useful.
So we can go
Thank you.
higher,
It
so
was.
we can get better coverage of CDK4.
Thanks.
That's why we can get better coverage. That's why when I did the
Ciao.
Thank you. Bye.
Thanks. Ciao. Thanks, Andres. I can't quite hear you still. I'm sorry, Andres, I've lost your audio. Still missing your audio there.